Hello my friends, welcome again to my video channel. Today we will start a new project, Spectrumanalyser from Advantest R3261B. As you see, we have a problem with the frequency stability. That's what the owner claimed. Let's have a look at it. As we can see, the frequency display is not stable. We have here a span width of 100 MHz. Left side is 50 MHz and this is 150 MHz. And this signal is from a signal generator. It's exactly 100 MHz. And 0 dBm should be centered, but it isn't centered as you see, and it is jumping, so the maybe a PLL or something like this is not stable. The owner said it appeared suddenly while he was working with it. And also the level, the amplitude seems not to be right, because 0 dBm reference is on top. There is an attenuator of 10 dB, but that's not relevant. I can switch the attenuator, and the attenuation, the input is calibrated, so the signal is always 0 dBm on the top. So we have, as I see, also a problem with the levels, with the amplitudes and with the frequency. So we will check first the block diagram and the schematic and look what the reason may be. A good approach is always a block diagram. That's the front end, the input section with the attenuator, low pass filter, and then we have the first mixer, EQ-tuned oscillator driver. This is the ETO, the EQ-tuned oscillator with VCOs and samplers to stabilize the frequency. There could be a problem, of course, which the control board. Then we have the second mixer, the second local oscillator, 3.84. This is gigahertz, not megahertz. The 4.6 gigahertz from the first IF is converted with 3.84 gigahertz to 222 megahertz. And then we have a third mixer, again with a 200 megahertz VCO, so the difference, this and this, is 22 megahertz. And then we have the fourth mixer, and this is the IF for the signal, for the video signal processing. There can't be the error. The error is most probably here in this section. One of these oscillators or the reference, also possible, is not good. Luckily, in the service manual there is a process, a scheme, what to do in the case of unlock. Event tolerance is in the center frequency setting, waveform is inconstant. That's exactly what we have. The amplitude is not mentioned here, but I think this is a consequence of the error we have. And then we have start, what to check, several pages, and I will do this step by step. But first, now I have to open the case. To open the case, we have to remove the feet on the rear side. It is a standard. They are metal, not plastic. I've seen many bad, defective feet on the rear side. They are broken because they are cheap plastic. Sorry, they are cheap plastic and they break over the years. But these one here are real sturdy and metal, I think aluminum or so. And now we can shift back the cover, take it away, and same we can do on the lower side. Here we have the inside view. This is a power supply. I think it's a good idea to start with the power supply. The manual on the screen here and also the printing tells me that the power supply supplies plus 15 volt. Oops, that's it. Minus 15 volt. What's going on there? Minus 15. And we have here plus 5 volt. Yes, it's also okay. This I think is a negative rail, minus 15 volt also. From these two, And additionally, I see there are derived 12 volt to the CRT. CRT works. And then we have additionally 8 volt and 10 volt to the RF section. And now Murphy, the RF voltages to supply the RF parts are on this motherboard, which goes underneath the power supply, so I have no access. I think they are connected to this plug, but I don't measure them here. I will measure them, the voltages in the RF part, when I check the oscillators and the PLL loops. But in general, obviously, the power supply seems to work. And now I will open this part here. This is a second and third converter and the 10 MHz reference frequency, the crystal, which should be in this range. Maybe this is an alignment point. I have to remove all these small screws. Okay, it's a job for someone who is patient, and I will start. And by the way, whenever you do such a job, always collect the screws in a box. I can't tell it often enough. When I get some equipment on the bench, in general, screws are missing. Don't understand why, it is not so difficult to collect them, but obviously some guys are not able to do this. The sheet is removed. It looks very nice, very good construction, perfect shielding with a braid, as it should be. This is the reference oscillator, 10 MHz, and the output here is connected. It's under this cable. It's pin 9, P9, but we should have 10 MHz, and it is stated in this scheme here. You scope the measure third converter P9, whether there's 10 MHz with 3 volt peak or not. That's what we will do now. And as we can see, we have here a perfect signal, 10 MHz, 3 volt peak. The probe has 10 by 1, 100 millivolt times 10 for 1 volt per division. So the reference frequency seems to be okay. And this is very close to this picture, as it should be. In the next step, this scheme asks for measuring the third converter, whether it is locked at 200 MHz, as a level should be 4 dBm or more. This is a test point, checkpoint 2, as it is. Use a feed probe. Well, I use a feed probe. It's my good old Tektronix P6201, and it's connected to my scope in the background. And there we can see the feed probe, and we have a 500 millivolt per division, so we have approximately 1.5 volt peak. So this is a level of more than 4 dBm, and the frequency is shown here. It's exactly 200 MHz or 199.99 something, but it is stable. That's important. There's no jitter, nothing, so I can say this is also yes. Also yes. And we can continue. After the successful check of the third oscillator, third converter, now we come to the second local and mixer, and this is rather difficult to open the case because the total RF block has to be taken out. There are 5 screws, 1, 2, 3, 4, 5 screws, which has to be taken out. That's easy, but there are 2 additional screws where the whole unit is screwed to the frame. This is the output here, and to get access to these 2 screws, this and this, it's necessary to take the front panel out. But to take the front panel out, it's necessary to remove 3 screws and another 3 screws. It is very, very user friendly, and now we can swing it out as far as it is necessary. In the manual here it is described to use extension cables. I don't need extension cables because this cable is long enough. It's a power supply. Here we have the power supply. This is a PSU unit. Only this cable has to be unplugged. I will replug it again. And then we have the output of the second oscillator. It is shown here. There are three slots. Don't know whether you can see them. I'll make some light. Here is one, here is one, and here is one. And in one of these slots there's a connector where we should use a spectrum analyzer. Yes, we need a second spectrum analyzer to connect the cable to the output. And this plug here I have seen, sorry, this one, the lower one, this one, it is located this way, or better said, it is so, this way. It's an Smb connector, not SMA, it's Smb. What's the difference? Well, Smb is only plugged. It's a connector like this. I have an adapter homemade. I don't know where I needed it, but now I have it. It's a small plug. SMA is a little bit different, and it is screwed. Anyhow, I can plug in the Smb onto the output. I plug it in. It's plugged in now, and then I can check the second LO signal, which should come out here. It's a 3.84 gigahertz output, and for this purpose I will connect my spectrum analyzer, switch this unit on, not to cause any short here. I have to look to be a little bit careful, but this will be the next step, to connect my analyzer to this output. Additionally, I added a ground connection between this block and the chassis. Of course, there is enough ground connection via the braids of the coax cables, but additionally it's not bad to have a connection to ground, because it's not the best idea to feed the supply currents over the braid. Well, this here is the input of my analyzer, this is the output. Now I connect both together and switch it on. Oops, I have to be careful not to cause a short. By the way, it's connected via an isolation transformer. Okay, picture is present, and now I should measure here a 3.8 gigahertz signal. And we have the signal 3.84 gigahertz, and it is stable. The resolution is 5 megahertz per division, so totally we have 50 megahertz. I will increase the resolution a little bit. Wrong direction. 500 kilohertz. 100 kilohertz per division. And we see the signal is stable. It is not rocking around. The original picture had a frequency jumps of several dozens of megahertz. Okay, it is locked now, phase lock. I will unlock it. But even in the unlocked condition, it's unlocked. I can see here no frequency jumps. So the second oscillator is also okay, and I will reinstall everything. On the next sheet we have to check the signal of the tuned oscillator of the synthesizer. The test point P15, and there should be a signal of 205 megahertz, more than plus 14 dBm, and we should use a spectrum analyzer, so that means a 50 ohm impedance. I will use this probe. It's a times 10 probe, 500 ohms, so the expected level should be a little bit more, but then we have to add, of course, factor 10. This is 20 dB. And the power, and we measure now on this pin. This is here the output of this synthesizer part here, a frequency of 205 megahertz. And here obviously we have a problem. The level I'm measuring here is minus 30 dBm. Top line is 0 dBm. I will make a better picture in a moment. Minus 30 dBm, and I have to add 20 dB, so the signal is minus 10 dBm, and it should be plus 14 dBm. So I'm missing here 24 dB. 24 dB. Maybe there is a fault in the synthesizer part. I will show you close up of the picture. Here you have the signal with stray coupling. When I move the probe around this point and when I connect it directly to the point, we can see the signal. It's roughly, or rather exact, minus 30 dBm. We have to add 20 dB for the attenuation of factor 10. Voltage 10 is 20 dB in power. This means we have a signal of minus 10 dBm. And we should have a signal of plus 14 dBm. As we have it stated here, more than plus 40 dBm, I have to say no. Q1, Q2, failure. Okay. I will do a counter measurement with my scope to realize whether it's really okay, or whether I'm doing here a wrong measurement with my analyzer, but the analyzer is calibrated and I'm rather sure there is no problem. Here we can the signal. In the right upper corner we have the frequency 205.24 megahertz, and the amplitude is 200 millivolt peak. The attenuation of the probe is considered in the screen because the probe is coded, and there's a pin. When I take out the probe, when I remove the pin, you see we have now 10, and when I connect it again we have 100 millivolt. So it's okay. Again, just to show it, 200 millivolt peak, and now we can calculate. The calculation is rather easy. 200 millivolt peak is 100 millivolt peak, or 70 millivolt RMS at 50 ohm. It's 98 microwatt, or let me say 0.1 milliwatt. This is minus 10 dBm. So this result is also okay and in line with the measurement with the Spectrumanalyser. And now we are here at the point to say no. Plus 14 to minus dBm. This is a little bit more than any tolerance. This star here shows the picture on the analyzer, which we should expect 14.6 dBm or so in the peak. We don't have, so I think there is a difference of 24 dB, and this is a little bit too much. This is more than tolerance and more than can be accepted. So I think we should have a look at the failure here, transistor Q1 or Q2. Sorry, Q1, Q2, as it is stated here in this paper. Before we continue looking for the problem, a short test. I will inject the signal exactly in the test point where we have seen the weak 205 megahertz signal. So I've set my first generator to 205.025 megahertz. That's exactly the injection frequency, which should be there where we have measured a very low level. The generator is set to plus 20 dBm, 100 milliwatt. That's the maximum the generator will supply, but it is sufficient according data sheet of the analyzer service manual. Here my second generator is connected with a 100 megahertz signal, 0 dBm. We have the jumping picture, span width is 100 megahertz, center is 100 megahertz, 0, 100, 50, 100, 150. Span is 100 megahertz, same picture as in the beginning of the video. We have the unstable picture, and now I connect the signal generator with a 205 megahertz to the test point with the capacitor, of course, isolation capacitor. Now the picture is stable. We have till a loss of 20 dB. Don't know why. It's another topic. Picture now is stable, but it is not accurate. It is ways off. And the next problem is when I tune it, when I tune the center frequency. You can see here slowly, slowly, slowly. Nothing happens. I had a stability problem. Here you see. The center frequency jumps. This is not normal. I only vary the frequency by some megahertz. This is okay. But maybe we have a problem now because I have two frequencies here. One with the right frequency, 205 megahertz, and there's a second frequency, of course, which is not exactly the same. Some dB weaker, so I don't know what's going on there, but it's a proof that we have a problem with the level of the 205 megahertz. So I will continue now my search on this circuit on this PCB. I was checking around at this part, which is a 400 megahertz PLL unit. This is a block schematic. We have here the output P15, which is too weak. Two transistors, Q1, Q2. There's a lock tuned oscillator on off. This is not relevant here. The signal was okay. Here not. It was too weak. 20 dB missing. And this is this part here. This is a transistor Q2, the power transistor, filter, trim caps. And here the signal was too weak at the local output. This goes to the sampler for the tuned oscillator, for the PLL to the YTO. I was poking around with these trim caps, touching them, and suddenly I had a full signal. So I think the problem was that one of these two trim caps, I think this one, the green one, had a contact problem. And I show it in the schematic. You see I poked around with DC voltages. This part was okay. The transistor, it was controlled by this lock YTO. It was switched on as expected in this mode. We had a 15 volt, 14 volt and 12 volt over this coil. Okay, it's due to the high frequency. Here I measured 0.33 volts. Suddenly this jumped up to 0.84 volt DC. This goes to the local. The local goes to the sampler. And when I measure the output power now, I have a full 20 dBm, more than 14 as it should. I show you. Connected again my 10x1 probe for 50 ohm system. That means 20 dB attenuation. But now we have full 0 dBm plus 20 dB attenuation here. So we have a signal of approximately 20 dBm. Expected here is more than 14. Up to now we had no. I tweaked around with the capacitor. Now we have the yes. So we can continue in this scheme. But first I will make a check whether the frequency now is stable in the display. Again, we have a 100 megahertz signal, 0 dBm. It is 0 dBm, yes. Now it is 0. Now we have full amplitude. Reference is 0 dBm, top. That's okay. But the frequency still is jittering. We have a width of 100 megahertz from 50. Center is 100 and to 150. So span width is 100 megahertz, and the center is 100 megahertz. This one should be centered here. It is not, still jumping, so we have to continue in our search. But one topic is now clarified, the level is okay. I think this was the influence here. I really don't understand why this level, which goes to the sampler and which goes to the synthesizer of the Yig-tuned oscillator, has an influence on the amplitude. I really don't understand it. But anyhow, we see there's another culprit. The next two steps I had to measure are a little bit suspicious. The output of the Yig-tuned oscillator synthesizer, the frequency should be 38 megahertz. Level more than -7 dBm, I measure -10 dBm. Okay, could be a tolerance. But the next checkpoint, P7, it's the output also of the synthesizer. Same frequency, another checkpoint, it should be more than -10 dB. I measure -20 dBm, so here's a difference of 10 dB. Here only 3 dB, but here is 10 dB. I'm not sure whether it's a measurement error, but I'm sure it's not one. So I think there could be a problem. I continue and make the next measurement, the next check. Pin 5 and pin 6 of RF control board has to be shorted, and then they measure the Yig output frequency. It should be 4096 megahertz. It's just one line, short circuit pin 5 and 6 of RF control. Nicely written. But to do this, I had to remove the side panel here. These two plungers which hold the board in place. It is here, and this is the RF board. I had to take it out to get access to the pin, and this is the pin where I have to short circuit pin 5 and 6. Pin 5 is ground and pin 6 is the output or input for the Yig-tuned control. So when we shorten it, the oscillator should run into one limit, into one end, and then we have to measure the frequency and see whether it locks. And I think this is an important measurement. Maybe we have a problem in the Yig oscillator because the level are a little bit low, so maybe there's a problem. So first I will shorten pin 5 and 6 here on this connector. Here we can see the short circuit, pin 5 and 6, 1, 2, 3, 4, 5 and 6. They are shorted and now connected to ground, and then I will reinsert this board. The board, the RF control board is in place. Plugs are connected. This is a Yig-tuned oscillator and this is the output. And I will connect an adapter cable to this output and then measure the frequency with my analyzer and also with my frequency counter. The output of the Yig oscillator is connected via this adapter to the counter, and the frequency is not as specified. It should be 4.096. 4.09. The 6 should be a 9. It is 63 megahertz, and this should be 96. So the oscillator is approximately 30 megahertz too low in frequency. I'm not sure whether it is relevant in the moment. It is stated here in the procedure to readjust the VTO drive circuit. A replacement of the Yig-tuned oscillator seems obviously not to be necessary. Now I will connect this output of the counter to my Spectrumanalyser. And here we have the signal. It is 10 dBm. 10 dBm. There is no level stated, but I think that's okay. The frequency is very stable. The analyzer is not locked, it is free running. We have no jitter on the tuned oscillator. Everything is stable, nothing happens. So I think the VTO is okay. Just maybe a little bit of realignment. I have to look into the manual how it has to be done. But in general, the frequency is stable. It drifts a little bit away at the thermal drift, but 4.06 something, same as we had before. The frequency is not calibrated. I have to calibrate it here, but I didn't do it. In general, it is the signal as expected, extremely stable. The YIG oscillator is obviously okay. I'm happy with it. I feared that the YIG oscillator has a problem, but as I see, it has no problem. So whatever it is not the YIG oscillator. That's a good result, but still I don't know what the problem is. But not the YIG, I think. I have reinstalled the board again. Installed these plugs. The PCB is seated correctly now, or again. And what can I say? The analyzer works. Center frequency 100 MHz. The signal has 100 MHz from my signal generator. 0 dBm, spot on. When I tune the center frequency, when I go 10 MHz down or up, center is 110 now. 120, 130, that's all okay. When I go into the other direction, center is 90, 80, 70, 60 and 50. Here we have the zero response because the bandwidth is 100 MHz, and when I have a center of 40 MHz, then we have here zero. So I can move the zero response into the center. When I have here 0 MHz center frequency. Oh, sorry, was it again? I think it was me. Let's go center 100 MHz. I don't understand what's going on there. Maybe I cleared a fault, bad connection. When I removed and inserted the PCB again in the plugs, the connectors, don't know. Or it was with the YIG when I measured the YIG and reinstalled the plug again on the YIG output. I will observe it and see what happens. And now I think that's the end of this project. I will do some additional tests, some vibration tests, some temperature tests with my heat gun and my ice cold spray on various frequencies. By the way, in the moment we have here a 500 MHz signal. It's also okay. I will take out my gigahertz generator and check it also on higher frequencies, but I'm sure that it will work also very well. Amplitude and frequency are correct indications, bandwidth and so. I don't really know what the problem was. I strongly assume that when I took out this board, this RF board, control board, that there was a problem in one of the contacts. Or it was not properly seated, I don't know. Now it is in. I took it out several times to solder the short circuit of the two pins for test purpose, and then for intend to unsolder this bridge. Maybe this caused the fault to disappear. I'm really not convinced about it. So I will look for some other problems. By the way, the level problem we had in the last footages with the what was it, 38 megahertz, 38 megahertz generator, where I had 10 dB loss instead of 10 dB, minus 10 dBm, I have minus 20 dBm. This problem is still there, but I don't know whether it's really a problem or whether it's a question of tolerance. I'm not sure. Anyhow, I will stop my video here. I will talk to the owner how to proceed. I don't want to waste much more time in this project when there is no need for it, when you have a stable picture on all frequencies. I will reinstall everything, and then I hope that the analyzer will still work when the case is closed. It's some work. That's it now. For now, maybe we'll have a second video about this Spectrumanalyser. Stay tuned, stay healthy, see you on this channel.